friend, the Brian Mintz will give a 50 minutes talk, and some chairs are available here. And the title of his presentation is, "But how many baskets should you put your eggs in?" And your abstract states also that, understanding this topic even made one mathematician a multi-millionaire. And can a biologist be rich?
Possibly. Also, to Nobel Prizes, that's what these are. So, millionaire isn't going to do it for you. Maybe a Nobel Prize winner might.
Awesome. So please.
All right. So thanks everyone for attending. Hopefully, this talk will be of interest to everyone here. So the general idea of this is how to make decisions under risk, right? So in general, because of either our reality being non-deterministic, or at the very least we don't have perfect information on reality, each possible action we could choose is going to have a range of outcomes. And so if it was just one outcome, we would just pick the action that had the best payoff for us, the best results. But because it's whole distribution, it's maybe not clear how to compare them. For example, you can have one distribution in white that mostly has moderately good outcome as compared to another distribution in blue, which has a lot of better outcomes, but it also has worse outcomes too. And so we're going to try to see if we can use mathematics to think through this decision and sort of solve and find what the best distribution is. So we quantify these through random variables, and I never, was super comfortable with the formulas of random variables, so I prefer to think of them as like their distributions. So a random variable is something like the probability of the certain variable x taking values in between a and b, and there's some symbolic rules to work with manipulating these. We can sort of express this as an integral from a to b of this probability distribution with respect to x. So you can sort of think about these as densities, and if you integrate the density, you sort of get the mass or the probability an outcome will occur in any given interval. So that's sort of the basic tool we're going to be working with today. And sort of the types of people who have thought about this question are very diverse. You might think most classically, right, this financial people are interested in this, right? Which investment should we choose? Should we choose an investment that is more certain, but is not going to have as good a return? Or should we go for something that is a bit more random, but could get us a really big gain if it works out well? In addition, you don't just have to choose a single investment, but you have to balance between the multiple investments you have going on. And so there's this question of how you allocate your resources, in that case money, across different possibilities. And this same general principle about resource allocation applies in many other contexts as well. So for example, biologists have thought about this if you're thinking about how reproductive effort is distributed amongst offspring. So down here at the bottom, for example, I have this little cartoon about some animals sort of go on the quantity side, others go on the quality side, right? Insects typically have, a lot of offspring with little investment, versus things like mammals tend to have a few offspring with a lot of investment, right? So this whole continuum, and you could ask, why did they choose quantity over quality? And even though these are general patterns, there are some interesting exceptions for each. Lastly, I think everyone here as researchers is sort of dealing with this question as well, right? When you decide which project to work on, you have to choose between a more minor project that is likely going to get work, it's going to work out, it's going to get accepted, you'll have some small paper, or you're going to aim for a bigger project that could fail spectacularly, maybe nobody hears about it at all, it doesn't really work. And how do you balance between those two with your research effort? And as well as applying on the individual level about what projects we work on, that same question applies at the collective level about which researchers do we give resources to, right? So, who do we hire for our job? Do we hire the person who mainly does things that are safe and minimal, or the things that are exploratory and often don't work, but sometimes change the world? And who do we give funding to? Right, so this sort of same question occurs at these two levels, and in general, these are the kinds of problems I'm interested in, is where you have sort of individual dynamics over here and collective dynamics crossed over there, and sometimes there could be a mismatch, right? So what works good for an individual might be bad for a population, and just in this talk, we're going to look at how you optimize within each sphere, and then later work, right, say how do those two relate to each other. Right, so that's this last bullet point about society, right? All these decisions are not happening in a vacuum, right? Your decisions about risk are going to impact other people. So you can have fun things like the 2008 financial crisis in the US, where people's individual risk-making decisions ended up sort of constructively interfering to make this a giant cascade that really wrecked the social financial system. You could also think about things like insurance, where charity or altruism are the paying of some costs for sure to sort of reduce these extremely bad outcomes. So, for example, a lot of countries have like subsidized insurance, where people can the government is paying a cost to reduce the odds that somebody has something very bad happen and then can't afford treatment or becomes homeless or something like that. So again, this is a very general problem because they all sort of fit this question of how do you allocate your resources amongst different distributions and how do they compare. Okay, so as I mentioned in the talk, right, we know how to compare outcomes, but we don't know how to compare distributions. So most of the work in this tradition has sought to find the right number to assign to a distribution, because then the problem is simple. If you can compress the entire distribution to a single number, that makes the sort of sorting problem trivial. Just pick the largest number. And the number that we might take for granted nowadays is just the expected value, right? And this has its roots in the 1600s with Pascal format, the Bernoullis. These are the people who sort of created modern probability as we know it. And this is sort of like a weighted average of all possible outcomes by the probability. To go back to our density example, this is like the center of mass of this distribution. And you could say, okay, there are some bad outcomes with blue, but in general, it's centered higher than the white distribution. So maybe we should choose that one. This is actually not a complete answer because there's a lot of distributions that might have the center of mass. So it's a little bit unsatisfying, but it does have some nice formal justification. So sort of these early people thinking about topics like insurance and how these individual decisions scale up when they're spread throughout a population have this nice result, right? The central limit theorem, which is if you have a bunch of independent measurements and you add them all together, it doesn't really matter what your distribution looks like. In general, the thing that matters are going to be its expected value and its variance. And if you sort of add a bunch of them up, you can sort of see those two expected values drift further and further apart. And in fact, the distribution of outcomes is going to approach something that looks like this, known as the normal distribution. So really, it's a good answer that says expected value, maybe variance is all you really should care about, assuming you have enough things that you're adding together, and that those things are independent. But the problem is maybe you don't always add things together. So in 1956, an information theorist, Kelly, who's actually working at Bell Labs, sort of was thinking about this question about, let's say that some investment is a good decision, how much should you actually put into that investment? You probably should put all your resources there, but what level between 0 and 100% should you put in? And they have this nice interpretation of like maximal information rate in a channel. It's like the maximum growth rate of your resources, but really the fundamental baseline of this model was the idea that resources don't grow additively. They actually grow multiplicatively, right? So the sort of product is sort of going to be like the product from I equals 1 to t of some IAD random variable x, which is the same x every single time. Instead of adding them, maybe we multiply them together, right? You can think year after year, if you have 5 children, each of those children have 5 children, you don't have 10 grandchildren, you have 25 grandchildren. So multiplicativeness could be reasonable. And then through the magic of logarithms, we can translate this product into a sum. So if we look at the ln p, we're going to get the sum of the ln of x. And now we're back to the land of the central limit theorem. So once again, we can work if you want to maximize p, because the logarithm is an increasing function, you can maximize its logarithm. And then you care about the ln of x, not x itself. So this is saying that in some contexts, you might actually care about the expected value of the logarithm, not the base function. To help illustrate how these two criteria aren't always in agreement, you can imagine these two very simple random variables. One is not random at all, it's just 8. And the other one is equally likely between 1 and 16. The expected value is just the average. And here, since these are equally likely, you can just add them together and divide by 2 to get 8 for the first and 8.5 for the second. So under this criteria, you would prefer the second distribution. However, if you compute the expected value as logarithm, we could use any base because all logarithms are related just by rescaling. So let's use base 2 since these are nice powers of 2. This is 2 to the 3 and 2 to the 3. So the logarithms are 3 and 3. So again, this value is 3. Here the logarithms are 2 to the 0 is 1, 2 to the 4 is 16, average of 0 and 4 is 2. But now 3 is greater than 2. So we can see that for these two distributions, these different criteria are actually disagreeing with each other. So we have to sort of ask ourselves, what is the right context for it in? And the geometric intuition for this is you can think about what the logarithm is doing to these random variables. So here we would draw something that roughly looks like the logarithm. And because of this inequality known as Jensen's inequality, you can see that these like asymmetric contributions of variations up and down the random variable. Right, so here imagine this is just you start with some constant variable like 8, And you can imagine maybe you shift some of it down and some of it up equally. The way that you can measure this is sort of through the variance. It sort of is a nice symmetric way to measure variation. It's like a very natural extension of the expected value. But then when you take the logarithm of both, you see that the deviation down is more dangerous than the deviation up. So the downside is greater than the upside. And that's because this is a concave down function, so its rate of increase is sort of slowing down. So essentially the conclusion from this is variance is bad. If you want something more formal, there's a nice paper I can send, and actually I have references for these on my website, which says if you write x instead as 1 plus delta, the expected value of the logarithm, let me make sure I get this right, can be approximated as the expected value of these deviations, e of delta minus 1/2 e of delta squared, plus some higher order terms, which is a nice way of seeing, right, that, okay, the first thing that matters most is the expected value of those deviations, and then variance, which is related to these squares, is bad. That's why I have a negative number here. Okay, so we know variance is like not a great thing, and we have maybe some ways to think about it. But okay, just because variance is bad, that doesn't really give us a great answer to this question. So another sort of good landmark thing was sort of these results in 1952 by an economist, Markowitz. They actually got the Nobel Prize in economics for this so-called modern portfolio theory. And the idea for that was we definitely like expected value. So let's still maximize that. But we'll have some constraint that's like how much risk we're willing to tolerate. So we fix this sort of upper limit in variance and try to maximize the expected value relative to that. And what they did is they imagined this whole space of every possible expectation variance you could achieve. And they looked at these sort of level curves in that space and used Lagrange multipliers to find that at the boundary of that level curve, you sort of have this linear trade-off with the expectation minus some value lambda times the variance, right? So this is sort of similar to that Taylor series expansion. And so this is, right, the idea of bed hedging, that we're willing to lose some in our expected value if that has enough of a compensation for a decrease in the mean. So again, returning back to these, we see that, okay, we do have a higher mean in blue, but we have a lower variance in the white distribution. So if that variance is small enough, it doesn't matter if you have, a lower mean, the decreased variance may be enough to compensate for that. But again, how much is necessary for that compensation? It depends on lambda, and lambda varies throughout the space you're in. So that's one main contribution. The other main contribution they did was asking this portfolio question, where if you look at a random variable that's just the sum with some proportions of other random variables xi, you can just write this in matrix form. And the nice thing that pops out is that that variance term that we care about is actually dependent on this covariance matrix, which says how each of the changes vary with each other. So if you have one stock that's going up, if another stock is also going up, that's a good thing when things are good, but it's a bad thing when things are bad. And so this sort of correlation between them can be negative because it helps you do better in good times, but then you also do worse in the bad times. And so it's a little bit more variable of a strategy. So that was sort of a nice contribution. Yeah, I guess one thing I'll say, because I forgot to mention up here, we can again see that in this simple example, variance is bad, right? Because this has no variance, it's always 8. And this has more variance because it's between 1 and 16. So again, this sort of matches with that general picture we're developing. Okay, so variance is bad. We can maximize subject to variance. But again, what is lambda, right? This is not really a satisfying answer because you don't have one single best distribution. So one solution to this was proposed in 1974 by a biologist, Gillespie, and their idea was to sort of let the mean and variance co-evolve. So they considered these different organisms that could have the mean as one trait of their offspring and the variance in this offspring trait as another. And what they found is if you do some particular analyses, I think it was the fixation probability in this case, depended mostly on the expected value minus 1 over n times the variance, where n is sort of the population size. So it says in a larger population, maybe variance has less of an effect than in a smaller population. Sort of makes sense, because in a small population, it's easier to take over, right? If you have a bunch of offspring 1 year, that might be all you need. But if you're in a giant population, 1 year with a ton of offspring might not get you too much, because that ton of offspring could be a tiny part of the population. And so in general, sort of biologists have continued in this direction of thought, and they sort of split apart this sort of one idea of bed hedging as mean variance trade-off into these sort of different types. So the first is just conservative, right? Minimize variance. Variance is bad, we don't want that. The second is diversified, minimizing the correlation, right? So covariance is bad, so maybe that's a thing you can control. And then lastly is the sort of adaptive, which is a little bit different. And it's the idea that maybe organisms are somehow adapting to environmental cues. And so if they expect the next year to be, a dry year, maybe they're not going to invest as much as resources because they know all their offspring are going to not survive that year anyway. And so you see, actually, you have like this trade-off along multiple dimensions. And there's a really nice review paper on this a while back. Again, I have a reference for that on the slides on my website. They also identified, right, variance is a bit too coarse of a term. So they distinguish between within generation, between generation variance. And you can imagine if this is like a chart of the offspring over time, the between is over each year, what is the variance in offspring number of a particular strategy or an individual in the population. And the within generation variance is the variation across all individuals in your population. And so again, we can think back to the central limit theorem and realize that, right, this can apply either if you're repeating many times in time or concurrently at a given time. So you have to be a giant population one time step, or you could be like a single individual across multiple time steps. And again, there was some nice work pretty recently, I think in the past 10 years, that sort of saw these two different types of variation as connected on a spectrum based on the correlation. Okay, so that was all different ways of trying to compress this entire distribution down to a number and find the single best one. But there was some really interesting work sort of in the 1970s that said there may not actually be a best distribution after all. All of this, while it's useful, might somehow miss some important part of this question. So this is actually based on a statistical paradox that was noticed a few years earlier. And the idea is sort of framed as a game. You have these die, and player choose a die to roll. These die are fair, so each side is equally likely to roll, and the higher number wins. So I've drawn a couple die here. These die each have 3 faces, and the number of dots here are the number of dots per face. If you're bothered by dice having 3 faces, then you might not be a mathematician. Or you can imagine that dice have opposing faces with the same number. Again, this is a nice minimal example. It's in some sense the first time this interesting behavior occurs. So for example, if you played 0-3-3 against 2-2-2, right, this is always 2. So then 0-3-3 will win 2/3 of the time when it rolls a 3. And then 2-2-2 is going to lose to 1-1-4, or it's going to beat 1-1-4 also 2/3 of the time, right? Because it's always a 2. So if 1-1-4 rolls either of the ones, it's going to lose. Now, you might then expect that that this sort of relation on probability distributions, I'll just maybe write that a bit more formally. You can imagine, again, connecting it to this language over here, we can write this as a preference relation on random variables, where if the probability that x is greater than y is above a half, that is what we mean by x is being preferred to y. So you would say that I prefer 0-3-3 to 2-2-2, I prefer 2-2-2 to 1-1-4, and so most people would expect that you should also then prefer 0-3-3 to 1-1-4. But it turns out that's not what happens, and the way to see that is maybe to look at the reverse. When does 0-3-3 beat 1-1-4? Well, 0 is never going to win, so it has to roll 3. And when it rolls a 3, the other one has to roll a 1. So this happens 2/3 of the time and 2/3 of the time. The rolls are independent, so that's 4/9 of the time this one will win, which means the remaining 5/9 of the time this die actually beats that die. So we see this sort of cycle, like a rock, paper, scissors dynamic, where each one beats the next. And so we can't say, like, what is the best die here? If you say it's this one, it's that one, it's that one. So it just goes around and around, and there's no like unique best answer. So this is known as the paradox of non-transitive dice, because if it was transitive, you would have, if that's preferred to that, that's preferred to that, then it sort of, you have the preference of this to that, but these are not transitive. And connecting it to the title of the talk, mathematics is sort of quite general, so you can also think about, instead of these as being the faces of the die, as being different baskets you put your eggs in. This is something that organisms such as salamanders here do, or farmers, if you have like multiple. I don't know why you want to like carry multiple baskets full of eggs. That seems like a hassle to me. Anyway, so this says that this is sort of a biologically somewhat plausible scenario, right? You could imagine that the one basket surviving is like you maybe have a very harsh environment where you have a bunch of different sets of eggs and only one set of eggs survives. And then if you have 2 different organisms where this one survived over here and that one survives over here, whoever had more eggs than that is going to take over the population. So maybe it's like also very competitive. So this is like somewhat biologically plausible, and there's other like cool generalizations of this to multiple players, or actually you can construct these sort of non-transitive dice for like any graph, any preference graph you might want can be realized in this framework. So really cool thing. There's multiplayer extensions as well if you want to sort of not just 2 at a time, but 3 or 4 at a time. It's not really known beyond that because of some combinatorial explosions. And you can also try to look at like weakening this particular payoff comparison rule, because like this one is a little bit arbitrary, and I think indeed this is actually slightly more general of a feature. Okay, so what's the answer? There is none. And so open questions that have gone on since here is, for this entire talk, we've assumed that this distribution is 100% known, but really part of the problem with decision making is you don't actually know the distribution. And so there's been a lot of work about like learning theory about how do you decide, as you're reducing uncertainty in this distribution over time, where should you invest those resources? So this is stuff like the design of experiments and clinical trials, right? When do we invest more in a drug that has maybe been promising, but is not as likely to succeed as like another drug that we have better results for? And it really relies to this like explore or exploit dilemma, where you can either explore more treatment options, or you could exploit the best one so far and really be more confident about that. And it's sort of a general thing that's appeared quite a lot in my research. You could also look at numbers that include tail effects, for example, these like black swan events, right? If you have one year that's just entirely terrible, that could matter a lot more than the average behavior. And lastly, there's been a lot of really interesting empirical work, both by biologists, to see like a lot of this would propose for like desert annual plants that only live 1 year. There's been some more interesting work about like microbes, because there we can actually control the environment. And we can directly simulate the evolutionary process on a fast timescale to see if these predictions end up working. And essentially, there's been some debate over to what extent we are actually seeing bed hedging versus another explanation. Also, there was a Nobel Prize winner here as well when you think about bet hedging in humans. This was Kahneman and Tversky studying biases, and essentially they generalized this idea of the logarithm, where we said variance is bad. This is known in the psychological literature as like loss aversion. People care more about losses than an equivalent gain. And so then people have studied like how these functions could evolve, or in what ways they might be optimal. Again, something that I'm quite interested there. Maybe the last thing to mention in my talk is that as I said in the abstract, right, one mathematician, Jim Simons, was sort of inspired by ideas like this, and they decided to try going to Wall Street. This was in an era before we had a bunch of quants or mathematicians and physicists going to Wall Street. So at the time, it was a very novel thing, and the main thing that made their company work is that they hired not just like the typical financial people who knew how markets worked, but they hired mathematicians and physicists who are really trained on identifying uncertainty and arguing between what the better models are. And that was a strategy that worked out very well. They're now like a multi-millionaire. They're one of the main funding organizations for mathematics in the US. So, if you're not interested in like a Nobel Prize or any of these deeper philosophical questions, you might always just want to be a millionaire. I mentioned I have the notes for this talk, as well as more other fun things I've worked on my website. You can just Google Brian Mintz GitHub. I also have a QR code on my name tag. Yeah, surprisingly it's legible. All right,
Thank you.
I'm happy to take any questions.
Yeah, so the questions for the non-specialists. Yeah. Everyone's up this please.
How does Shannon entropy how do you this picture?
Yeah.
But I usually think what I would think is the measure of the distribution.
Yeah, no, that's very interesting, right? So Kelly was
Sorry,
information.
what is the question?
So to repeat the question, right? So, right, we have an information theorist, and one other quantity you might ascribe to distribution, other than its mean or its variance, is its entropy, right? This is like the sum of the integral of the probability times logarithm of that probability, and this relates to like how much uncertainty there is, and a lot of physicists care about this thing. I don't know. It's not typically been coming up in the bet hedging literature, so it could be another interesting thing that tells you other piece of information about the distribution that are relevant for this. My instinct would be it's probably pretty similar to variance, but yeah, I mean, Kelly was an information theorist, so right, the cool thing about their work is that they were interpreting information rate across a channel as like the maximum growth rate if you're betting on the signals coming out of that channel. So there is definitely a deep connection there, but I don't think it's been explored sort of as fully as some of these other ones.
Yes.
What you want is the best gain and the smallest risk, right? So, is there any objective function
by which you maximize it to obtain the best result.
Yeah, definitely. So, right, you could look at a function like this, which sort of combines those both at the same time. And right, this is a pretty broad literature because all these different people said maybe this objective function is the one that works best, maybe that's the one that works best. And something that I think is sort of interesting is this non-transitive dice example shows that sort of whatever objective function you choose, you're probably going to miss something because at least for certain types of environments, you're going to have this non-transitivity. So it says there's no like perfect answer. But this is actually a thing that I've been doing some research on. Hopefully I have a pre-printout shortly, and I'm happy to talk with anybody more later. But even though this shows like there's not like a perfect answer, I mean, you can also look like these all have 6 dots, right? So like there's okay, they have the same mean, so maybe like up to first order, indeed mean is still the answer, and this is just saying there's like a slight nuance on that story. But yeah, I think that the tough part about this is that each of these could be the right objective function in particular context, right? This is like if you have an additive fitness versus you have a multiplicative fitness, or in some contexts there may be no answer at all. So it really depends on the base environment you're considering.
The question is how to extend such general or a universal objective function exists or not. In the case of the simple mechanics, the kinetic energy minus potential energy,
Okay.
and such a variation principle always precisely describe the dynamics. And I want to know how extent this kind of simplification is possible in this field.
Yeah. I guess that's a good question. I think that's maybe not the type of question people have been asking in the literature here, right? They're mostly just saying, I want the most result. And so this may be an interesting separate question about, how well does this approximation work? And this like sort of point in here about large tails, that's really when you see this approximation breakdown, right? There are some random variables like a Cauchy distribution, which have like infinite mean or infinite variance. And so, just saying, oh, let's choose the mean, like that's not always a great answer because depending on the type of variables you're considering, you might have these like large tail effects that make things complicated. So yeah, I don't think people have looked at things in precisely that way, but it's definitely an interesting question to see to what like, okay, this answer is like wrong literally, but it's also somewhat right. So exactly how wrong or right is it? And when is it more wrong in some cases than in others?
Yes.
Hi, Brad. I have a question. So you emphasize the mean and the variance, and naively I just think variance is just a second order of the second order moment. And want to know, is it possible or meaningful to consider higher order moment to
Yeah, so you definitely could, right? So I think after that it's called like kurtosis, and then there's other fancy names. So, if you took more terms in this Taylor series, you would get a more accurate approximation. But I think the challenge is you sort of need this like reference distribution on your random variables, because as the previous speaker was saying, like, okay, maybe you can approximate pretty well, but like in what sense, right? Like if you assume the type of random variables you're considering are all looking a certain way, right? Like then, right, somehow you're trying to replace this thing that's comparing two things with a single number, but depending on which comparisons you're more likely to see, a different single number might be better. So I think it's sort of tough. So you definitely could do the third moment, and that would give you some information. But there's like another question of like, if you have to choose a number, if you have to compress this information down, and you're making some comparison function over some distribution of random variables, given that triple, then what is the best number? What's the best pair of numbers? What's the best triple of numbers? And that's definitely, again, not how the literature is tended to thought of it, but it's a question I'm very interested in.
Yeah, anyone can ask a question. So, I'm talking.
Especially in the middle column, I feel that implicitly you assume that you have a lot of trials and they are all independent, so that indeed you can everything summarize with the central limit here and the lower part. So well, in practice they are not, right? Maybe you don't have so many chances. They are not independent. Yeah, so again, another great observation. So one of the other extensions that I didn't mention here, I think it should be on the slides online, is that people have considered, right, these finite models as well, where you only have a few number of samples, because that can also change the picture. Right, for example, this is sort of interesting because we only rolled the dice once. You can imagine if we rolled the dice like 500 times and either added or multiplied or did some other aggregation function, that may resolve this non-transitivity. Not exactly. So not for these dice, but for other dice, they've been constructed where like
with 2 rolls, the order reverses, and with 3 rolls, it can reverse again. And so I think, yeah, it depends. If you have enough rolls, this sort of theory may be pretty robust. There are still some maybe edge cases where, okay, this theory doesn't say anything about what happens if the means are the same. Like, you then need to go on to a higher moment to get some other information to answer this question. But yeah, you've definitely identified an important part that, the number of iterations or the population size here is another very important aspect in answering this question.
Okay. And you can classify the problems into solvable or non-solvable ones. I mean, just solvable by just finding the best or likely the best solution.
Yeah, I'm thinking it probably would be solvable. I don't think the challenge from this problem is about optimizing any of these functions. I think the challenge is choosing what is the right function to optimize, right? So whenever you're trying to translate from these diverse, real world domains into a mathematical model, there's a bunch of questions about like, why is that a reasonable payoff function? Like for example, like this, something that looks really weird is this 2/3 would apply regardless of what 4 is. So if this was like 119 million, this would still be winning 2/3 of the time. And somehow if your offspring distribution is 119 million, it feels weird to say you're like losing to 222. Somehow that 9 million versus the last 2 should make a difference than if it's 4 versus 2, right? So I think within any instance, you can have a coherent theory and can solve it moderately easily. The harder question is, what is the right way to translate this application into a model? Once you have the model, okay, you're good. But that initial step is where a lot of the argument takes place.
Any other questions? May I ask a question? I think you explained a bit, but how this topic is related to your study. Are you going to get millionaire?
Yeah, definitely. Yeah, so we'll see. I think for me it's just fun and interesting to like draw on such a broad intellectual history. But one thing I'm really interested in is like population dynamics of this, right? So like this initial approach was like game theoretic, like what's the strategy I should choose? I'm more interested in like evolutionary dynamics of if you set this fitness function, what happens to the population over time? And I was seeing some pretty cool initial results on that, and hopefully I can in a little bit classify when different things occur based on the number of eggs and the number of baskets. And then more broadly to the societal question, I'm interested in types of things where you have some dynamics at the individual level, or how you optimize your own output, whatever that is. And then how do you optimize society's output, right? Individual welfare versus social welfare don't always agree with each other. And I think thinking through those tensions and how you can get a proper incentive structure to align individual motivations with societal motivations is very interesting to me, and hopefully also like important to solve societally, because we don't want everybody to be like doing their own thing and sabotaging each other, stabbing themselves in the back. We want people who in a certain society will be working towards the collective good.
Good. So yeah, let's thank the speaker. Yeah. Yeah, this concludes the coffee meeting, and have a nice afternoon.
Thanks very much. Oh yes.
There's going to be a career development meeting at 1:30 p.m.
Yeah. Here.
And we're going to have an informal discussion about publication.
That's very
Important. Yeah. Yeah. Oh, yeah. Thank you.